Hi, in this lecture video, I'll be discussing dissolved metal reduction, which is a type of selective reduction of alkyne to entrance alkene. So we have seen previously before that an alkyne may be reduced to an alkene, and it will be reduced to a cis alkene by doing hydrogenation in the presence of Lindlar catalyst. So here in this method right here, we are trying to investigate another way how to reduce an alkyne into a trans alkene in case the trans alkene is what we're going after. And it turned out that it's possible, and this method right here is called the dissolved metal reductions. So the reason why that we call this the dissolved metal reduction is because it actually consists of a metal that we dissolve in another polar solvent. So here in this case right here, the metal is sodium metal dissolved in liquid ammonia. And what this will do is that it will create a source of solvating electrons. And this electron right here are then added to the triple bonds. So therefore, this is basically a reducing agent right here. So when we combine sodium in liquid ammonia, it is creating the source of electron, and therefore it is a reducing agent. And please note to not mix this together. Sodium solid mixed with liquid ammonia is a reducing agent, versus when we have sodium and sodium amine right here, then this is a strong base. So these two reagents right here are different. The first one is the reducing agent versus this one right here. This is simply thus a strong base. So when we take our triple bond and react this with the dissolved metal reduction using sodium and ammonia, we'll be able to now convert this alkyne into an alkene in which the two hydrogen are then added on the opposite side. And that then make this two alkyl group right here on the opposite sides as well. And this would then be our trans alkene. And the mechanism of this reaction is as follows. So first, the sodium, when we dissolve this in liquid ammonia, it basically generates a source of electron. And here in this case right here, we can see the electron come from the sodium metal. This electron is then added to this carbon-carbon triple bond, in which that, so we can imagine that the pi electron in here would be broken. One electron go to each of this carbon. And now, one of this carbon with its electron radical is now combined with electron that is given up from the sodium to convert this into a negative charge. And this negative charge right here, once we produce already, then it becomes basic, and that will then come in and grab one of the proton from ammonia, and that's what we will have. Now the other carbon over here will then become a radical, and with one single electron on it. So after the protonation step, then this is what we'll have right here. And then another molecule of sodium will then donate another electron to this radical right here and convert this into another negative charge as well, into another anion here. And now this, once we produce this now become basic, and that can come in and grab another proton from the ammonia. So this is actually basic enough to be able to deprotonate the ammonia, because the pK of this is about 38, versus this corresponding pK here is about 45. So therefore, this is basic enough to deprotonate the proton from ammonia. And so, and the one thing in here that the important that discuss the stereoselectivity of this reaction is as follow, because it go back to this initial step right here. When the electron is then added to this carbon-carbon triple bond, then this group right here and this electron repel each other right here, and so are this R group right here. So therefore, to make sure that they have this most stable conformation, the two R group will then be on the opposite side, and this radical and this anion right here, this orbital with the pair of electron in it, will then be the opposite side. And then later on the next step, the hydrogen are then being added to this carbon and this carbon right here on the opposite side. But then this is the step right here that kind of set the stereochemical outcome of this reaction. And now let's try some of this example right here. So if we were to now take this alkyne and treat this with sodium in the presence of liquid ammonia, what will be the product? So again, we would then notice that this is the dissolved metal reduction right here, and we'll be able to make the trans alkene. So here in this case right here, we would have the isopropyl group on one side, and now the other group here will be on the opposite side, and the two hydrogen will then be added to the opposite side. So that will be the product of this reaction right here. And similarly, with when we take this this reactant on problem number 11 and treat this with sodium in the presence of ammonia, we'll be able to convert this triple bond into a trans double bond as well. So here in this case, the methyl group will be added on this one side, and the propyl group will then be added to the other side, and the two hydrogen being added right here. In summary, the catalytic hydrogenations and the dissolved metal reduction are the two ways how we can reduce an alkyne into the alkene. And now, depending on which types of alkene that we desire, we can either use the little catalyst in the presence of hydrogen if we want this cis alkene right here, versus if our goal is to synthesize the trans alkene, then we'll be using the dissolved metal reduction method. Now, if we were to be using hydrogen in the presence of a platinum or another types of metal catalyst, then we'll be able to reduce this alkyne all the way to the alkene. And again, it depends on which method that we use. We will be able to obtain the desired product that we want. So now let's try some practice problem right here. Identify the reagent that you would use to achieve each of the following transformation. So on the first one, we are taking this and now converting this into a cis alkene. So we have an alkyne that now being reduced into a cis alkene. So here in this case right here, which set of reagent that we will have to use? So in this case right here, we know that we have to use hydrogen with the linear catalyst. And if we were to convert this alkyne into a trans alkene, then we have to use the dissolved metal reduction method using sodium in the presence of liquid ammonia. And as for B, if we were to have an alkyne and we want to reduce this to, in this case right here, this is a trans alkene right here, then again we have to use the dissolved metal reduction method. And if we want to convert this all the way into the alkane, then we'll be using hydrogen with along with a very strong metal, such as platinum, and this will reduce the alkyne all the way to the alkane.